All right. So, although this is admittedly a short question, it's got a little bit of messiness to it, so let's just dive on in. The statement reads, check that the potentials of a point charge moving at constant velocity satisfy the Lorentz gauge condition. All right. So, let's recall that the Lorentz gauge condition is divergence of A is equal to negative mu naught epsilon naught dv dt, where v was the scalar potential. And, we know that the potential for a moving charge here is given as A r of t, as this thing here, which is really gross, and v is equal to that thing. Again, we see that it follows that kind of relationship where A was equal to v over c squared times the vector or the scalar potential. So the forms kind of mimic, but those denominators are really, really gross. So that's our point now, is that now we need to take the divergence of A and see if that's equal to the 1 over c dv dt of 1 over c squared dv dt of the scalar potential. With that being said, the divergence needs to move through. We have v dotted with the divergence, as that's the only scalar part of the vector potential left. So we'll save that for later. And now it's just up to us to take the gradient, so to speak, of all these wonderful components here. And as you see, what we have is that square root needs to be written as a fractional power. So we bring a negative 1/2 down. And then we have a bracket. So that goes to the negative 3s power. But then now we have to use the chain rule and apply that gradient to everything on the inside. Okay, well, now we're getting really gross. Fair enough. So now that we have that, what we need to do is apply the gradient to everything on the inside, and then we just take the v width, because everything is in the negative 3 power is just a constant. So apply the gradient to everything on the inside, and we see we get several product rules and power rules with chain rules. So that factor 2 comes out front. Then now we have the gradient of negative r dot v in purple. C squared minus v squared is a constant, so who cares? Now we are left with that gradient of r squared, which is perfectly fine, which is in blue. But then c squared t squared was a constant with respect to the spatial dimensions, so that goes to 0. And I tried color coordinating that as best I can. Okay, however, this is a mess, so we're going to take we're going to use the gradient of a dot product, which is given as this nasty expression. No wonder we like to skip this step in our calculations, but we know here that when we apply the purple to it, we see that we get a lot of cancellations, because, the gradient cross v goes to 0, gradient cross r goes to 0. Again, just the cancellations of the same factors. We saw that before. And then it also helps that v is a constant, so taking the derivative of a constant goes to 0. Similarly, the curl of r is 0, so we saw that back in chapter 1. And this reduces really, really fast. So what we're left with is gradient of r dot v is equal to v dot the gradient applied to the vector r, which we kind of saw earlier. That just gives us back out the vector v, and here's how we see the component-wise doing that. Similarly, we have gradient of r dot r, which is, we could rewrite that using the product identity here, and we see that we get del cross, or the curl of r, again, goes to 0. Then we get 2 of those, and we also get 2 of the r dot r's. So if that's the case, the 2 r dot del applied to r just gives us 2r, and we're cool enough to simplify that. So I put that negative 3s power to the denominator to try to save space, and I put the results for purple and blue in, and we see a lot of cancellations again once we try to tidy up as much as possible. And apply that dot product that was originally in the divergence. So now it's just a matter of simplifying as much as absolutely possible. It's tedious work, but we got to do it, and then we see what the final divergence of A is, and we see that we get a C cubed there. Now, if we check for the other part of the Lorentz gauge condition, we see that we have a negative mu naught, epsilon naught, dV dt. So given that dV dt, we do the same thing. Again, we're going to have to apply the chain rule. So, go on the square root, make it a negative 3/2 power, then go on the inside, then tag along everything you need to with the respective chain rules. Again, a holistic mess, of course, cannot have nice things. Tidy up as much as you can. And then you see we're left with a mu naught q c cubed over 4 pi with the same numerator, same denominator. That's a typo. That should be a positive 3/2 or exponent in the denominator. So, typo there. But yes, everything else looks to be according to plan, and we are good to go. Just, get rid of the negative signs whenever you write it down.